Hi everyone, in this video we're going to learn how to both find and classify the stationary points on a curve's length. And we'll be learning how to do this without a calculator by studying the sign of the function's derivative. And we'll be using a sign table to do that. The function we'll be working with is the one we see here, f of x, which equals to 3x plus 12 over x. And just to make sure we're all clear as to what we're about to learn here, let me quickly show you this function's graph. Looking at this curve, we can see that it comes in two branches. Indeed, we have one branch here in the first quadrant and a second branch here in the third quadrant. Furthermore, we notice here that this curve has two stationary points. Indeed, it has a local minimum right here with coordinates 2, 12, as well as a local maximum with coordinates -2, -12. And so what we'll know how to do by the end of this video is both find the coordinates of these 2 points, so those will be the same as the coordinates we see here, as well as show or prove that we're indeed dealing with a minimum and a maximum. And all of that will be done without looking at the graph or without touching a calculator. So let's get started. I'll just get this graph out of the way. Now, the first thing we need to do here is to find the stationary points. And to do that, we start by solving the equation f dash of x equals to 0. Solving this will give us the x-coordinates of the stationary points. And since this equation involves the derivative, f dash of x, we need to differentiate the function we have here. So let's go ahead. F dash of x is equal to the derivative of 3x, so that's 3, plus the derivative of 12 over x. And the derivative of 12 over x is -12 over x squared. So the derivative turns into 3 minus 12 over x squared. And here I should say, notice that I went straight from 12 over x to its derivative -12 over x squared. To do that, I used the following result, which is definitely worth making a note of if you don't already know it. As soon as we have to differentiate a over x, then its derivative will always equal to -a over x squared. Using this result, we can quickly state that the derivative of 12 over x is -12 over x squared. That being said, I carry on. Remember, we have to solve f dash of x equals to 0, which is the same thing as solving 3 minus 12 over x squared equals to 0. And now to solve this equation, I'm going to write the entire left-hand side over x squared. For that, I multiply 3 by x squared. And this turns into 3x squared minus 12 over x squared equals to 0. Now, the only way this fraction will ever equal to 0 is if the numerator equals to 0. Indeed, the denominator plays no part at all in this equation. So solving this equation is the same thing as solving 3x squared minus 12 equals 0. We're now faced with a quadratic equation which we can solve by factoring, and I'll start by saying this is the same thing as 3 times x squared minus 4 equals to 0. And now looking at x squared minus 4 as x squared minus 2 squared, I use the difference of two squares formula and state that this is 3 times x plus 2 times x minus 2 equals to 0. And we're now faced with a product of 3 factors which equals to 0. So either 3 equals 0, which isn't possible, or x plus 2 equals 0, which would lead to x equals to -2. And of course the other possibility is if x minus 2 equals to 0, which will lead to x equals to 2. And so these two values of x are the solutions to f dash of x equals to 0. And they're the x-coordinates of this function's stationary points, which you may remember are the same coordinates as on the curve we had seen at the beginning. Now that we have the x-coordinates of the stationary points, we need to calculate the corresponding y-coordinates. And for that, we plug in each of these two values back inside the original function we had. And I'll start with x equals to -2, and I'll calculate f of -2, which equals to 3 times -2, plus 12 over -2. That's equal to -6 minus 6. In other words, f of -2 equals to -12. And so -12 is the y-coordinate of the stationary point at x equals to -2. I now do the same for x equals to 2, and so that would be f of 2, which equals to 3 times 2 plus 12 over 2. That's equal to 6 plus 6, and finally, f of 2 equals to 12. And that's the y-coordinate of the second stationary point, whose x-coordinate is 2. And so now we can say that we have found this function's stationary points. And they have coordinates -2, -12, and 2, 12. Okay, now that we've found the stationary points, we move on to the second thing we had to do, and that was to classify them. And so I'll write a 2 at the top here. There we go. Now, as I said at the beginning of this video, to classify this function's stationary points, we're going to study the sign of this function's derivative. And we're going to do so using a sign table. And to do that properly, the first thing we need to do is write the derivative f dash of x in its fully factored form. Here's what I mean. We know that f dash of x is equal to 3 minus 12 over x squared. And so just as we had done in our working here, I'll go ahead and say this is equal to 3x squared minus 12 over x squared. And finally, to write this in fully factored form, I factor the quadratic that we have on the numerator. And we had done that earlier on right here. And so using that result, we can go ahead and state that f dash of x is equal to 3 times x plus 2 times x minus 2. And all of that's written over x squared. And in fact, I'll go ahead and box that derivative written in its fully factored form. There we go. Okay, now we're ready to construct a sign table, and you'll see why it's so important to write the derivative in its factored form. So the first thing I do is draw a table, something looking like this. And the very top row of this table is used for x. More particularly, we use this space here to indicate two things. First of all, we'll use this space to show the domain of the function. So that's the domain of f of x. Secondly, we'll also indicate any values of x at which the first derivative, f dash of x, equals to 0. In other words, any values of x at which there is a stationary point. Now, this function f of x is perfectly well defined for all real numbers except 0. Indeed, since we can't divide 12 by 0, we need to exclude 0 from the domain. And to show that, I write negative infinity on the far left-hand side, as well as positive infinity on the far right-hand side, and right in the middle, I'm going to write 0. And to indicate that 0 needs to be excluded from the domain, in other words, that f of x isn't defined there, I draw two vertical lines directly underneath 0, like so, and I hatch the area between them. Now I add the values of x at which this function had stationary points. Remember, those were -2 and 2. So I write that here, that's -2 and 2. Now I create the columns inside my sign table by drawing vertical lines leaving those two values of x, like so, all the way to the bottom of the table. Okay, now we're ready. Each of the factors we have inside f dash of x will create a new row inside our sign table. And we're going to study the sign of each of those factors. So let's go ahead. The first factor is 3. And so I write 3 on the far left-hand side here, and I create my first row, like so. Now, in each of the 4 cells we have here, I need to indicate whether the factor we're dealing with, so in this case 3, is positive or negative for x values inside the interval written above it. And in the case of 3, well, it really doesn't matter what x does, 3 will always be positive. And to show that, I write positive or plus, 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 and plus. Done. Now I look at the next factor. That's x plus 2. And so I write that here, that's x plus 2. And I make my next row. There we go. Now, x plus 2 will be equal to 0 if x equals to -2. And so I write that 0 right on the vertical line that I have here, like this. Now, for the first cell, we're dealing with x values between -infinity and -2. And you can go ahead and check, but if you replace x by any number between -infinity and -2 excluded, you'll get something negative. And so I write a negative symbol or a minus sign right there. For the second, third, and fourth cells, well, all of these x values are greater than -2. And again, you can check, but if you replace x by anything greater than -2, then x plus 2 will be positive. So I write a plus sign here, a plus sign here, and a plus sign here. Done. I move on to the next factor, x minus 2. And so I write that here, that's x minus 2. And I make that row. There we go. Now, x minus 2 will be equal to 0 if x equals to 2. So I write a 0 right here on the line. For the first 3 cells we have, we're dealing with x values that are all less than 2. And you can go ahead and check, but if you replace x by anything less than 2, then x minus 2 will be negative. So I write negative, negative, and negative. Now for the 4th cell we have here, we're dealing with x values that are greater than 2. And if x is greater than 2, x minus 2 will be positive. So I write a plus sign right here. Finally, I move on to the last factor, which is the denominator I have here, x squared. And so I write that x squared. And I make my row. Now, x squared would equal to 0 if x were equal to 0, but remember, that's a forbidden value, so we're not going to bother writing 0 here. For any other value of x, x squared will always be positive. And so I can write positive, 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 and positive. Done. We've now taken care of all of the factors in f dash of x. And to highlight the fact that I've written all the factors, I make a double line here at the bottom. And so underneath all of this, I'm ready to study the sign of the derivative f dash of x. And so I write f dash of x here. And I create a new row, like so. Now, the first thing I do on this row is indicate the values of x at which f dash of x equals to 0, which tells us where the stationary points are. And f dash of x will equal to 0 when either x equals to -2, so I write that here, that's 0, or when x equals to 2, so I write that here as well, that's 0. Next, to find out whether f dash of x is positive or negative inside each of these cells, all I have to do is consider the product of all of the signs I see above each of them. Here's what I mean. For the first cell we have here, in other words, for x values between -∞ and -2 excluded, f dash of x will be positive times negative times positive, which will be positive. In the second cell, for x values between -2 and 0 excluded, f dash of x will be positive times negative times positive, which will be negative. For the next cell, that's for x values between 0 and 2, f dash of x will be positive times negative times positive, which again will be negative. And finally, for this last cell, so for x values greater than 2, f dash of x will be positive times positive, which of course is positive. Done. We now know the sign of the derivative for all x values inside its domain. And as such, we could stop there. But what I like to do is add the last row we have here, and as you can see, it's quite a tall row, inside of which I write what f of x does. That's the original function. And here's the whole idea. For this first cell, I look at the sign of the derivative above it, which is positive, and that tells me that f of x must be increasing. So I draw an arrow going upwards, like so. For the next cell, I look at f dash of x above it, which is negative, and that tells me that the function must be decreasing, so I draw an arrow going downwards. I carry on. For the next cell, if I look at the derivative above it, it's negative. And so f of x must be decreasing, so I draw an arrow going downwards again. And finally, for the last cell we have here, if I look at the sign of f dash of x above it, it's positive. And so f of x must be increasing, so I draw an arrow going upwards. These arrows help me quickly classify each of the 2 stationary points. Indeed, I can now see quite clearly that the stationary point when x equals to -2 is a maximum. And in fact, I can even write that in my table. This is a maximum, so I'll just write max. And I can add that to the coordinates here. This stationary point is a maximum. Done. For the next stationary point when x equals to 2, we can see quite clearly now that we're dealing with a minimum. And so I can write that as well. That's a minimum, so I'll write min. And again, I can label the stationary point we found earlier on. There we go, minimum. And now going back to the graph that I showed you at the very beginning of this video, the results we have here confirm everything we had seen. Indeed, the branch in the 3rd quadrant increases, reaches a local maximum with coordinates -2, -12, and then decreases. Then, moving on to the branch in the 1st quadrant, we can see quite clearly that it decreases, reaches a local minimum with coordinates 2, 12, and then increases. And so we've reached our objective. We now know how to find and classify the stationary points on a curve by studying the sign of the first derivative. And that's it for this tutorial.